Alright, this is 4.7, problem number 9. We're using the intermediate value theorem and Newton's method to find an intercept with the x-axis. So, when I did the mean value theorem video, I also covered the intermediate value theorem because they're so very similar. If you haven't seen it, I recommend watching it, but I'll give a brief description of what the intermediate value theorem states here in a second. So the question is, we have some function of x that's equal to x cubed plus 3x minus 5, and they want us to find a root, or what we could call a zero as well, on the interval 1 to 2. If yes, so in other words, if the intermediate value theorem proves there's a root, if yes, find the root to 5 decimal places. So we know we're interested between x equals 1 and x equals 2. We know what the function looks like. Let's look at what the intermediate value theorem states. So remember with the mean value theorem, we were looking for continuity and differentiability because we were looking for times where the slope matched the secant line. Well, that's like the next step from the intermediate value theorem. So let's reel it back a step. For the intermediate value theorem, we only need continuity. We do not need differentiability. So what the intermediate value theorem states is if f of x is continuous along an interval ab and has outputs fa and fb, that any output c such that fa is less than or equal to c and c is less than or equal to fb, or fa is greater than fc and fc, or if fa is greater than c and c is greater than fb, it must exist. What does that mean? Well, that means if for example, I'm curious if my function crosses this point y equals c, and if I look between, let's say, x equals 0 and x equals 2, if I plug in f equals 0 to my function, and let's say I get 1, and I plug in x equals 2 to my function, and let's say that I get 3, and let's say I'm curious if c exists anywhere in that interval. So I'm looking for any point where my graph crosses c. Well, if the graph is continuous, which means that I never pick up my pen while I'm drawing it, then there must be a point in between these intervals where c exists. Like in this case, a is 0 and f of a is 1, and b is 2 and f of b is 3, and I'm curious if c occurs at 2, if there is a c that exists at 2, and yes there is. And so it's pretty straightforward logic. We'll go through it with the 0 up here. So we're going to plug in our endpoints, 1 and 2, into our function. So f of 1 is equal to 1 cubed, which is 1, plus 3 times 1, which is 3, minus 5. And this gives us a minus 1, right? 1 plus 3 is 4, minus 5 is minus 1. So we know that when x equals 1, our y output equals minus 1. So there's an ordered pair 1, comma, minus 1. Now we're curious about f equals 2 when we plug in 2 to f. 2 cubed is 8, plus 3 times 2 is 6, minus 5. Well, 8 plus 6 is 14, minus 5 is 9. So we've got a positive value, and so we know that when x is 2, y is 9 for our function. Now we're curious, is there going to be a root or a 0, some point where the function intercepts the x-axis? And it does not matter what the graph looks like as long as it's continuous. For example, it could look very polynomial-esque. We still see that there's going to be a 0. It could even be non-differentiable. It could have a hard edge like that. But because it's continuous, no matter what you do between those 2 points, if it's continuous, the graph f of x must cross the 0 line. So we've proven that there is definitely a 0 for whatever this function is using the intermediate value theorem. Now we're going to use Newton's method to figure out what that 0 is accurately to the 5th decimal place. Okay, so what does Newton's method look like? It looks like xn plus 1 equals xn minus f of xn over f prime of xn. And I've done a few videos on this, one proving where the method comes from, which I recommend watching, And in the last video, which was about 4.7, number 6, finding zeros. And for that reason, I'm not going to walk through this method because it is tedious, it's full of computation, and computers can do it for us. Once you understand why it works, why bother using it if a computer can use it for you? So, but I did show how to use it in a video about Newton's method and in 4.7 number 6. And I also recommended in 4.7 number 6 that you use a Wolfram Alpha widget that has to do with Newton's method. So if you look that up, you'll find, if you look up Newton method approximation calculator, the second hit will be Wolfram Alpha widget, Newton's method calculator. And for that, we can now just plug in our function, x to the 3 plus 3x minus 5. And let's go ahead and guesstimate. So we do need to choose an x1 point, right? We always have to choose an x1 point. And I just went ahead and chose x1 to be 1.5. Because 1.5 is between 1 and 2. And it's about the best guess I had. So just make sure it's in the interval that we're actually looking at. And then I went ahead and hit solve. And it gave me an answer that's well beyond the 5th decimal place of, so the intercept here, the x-intercept, x sub int, is roughly equal to 1.15, 417, and that's to the 5th decimal place and rounded. And we'll go into our My Math Lab assignment, and yes, the given function has a root between 1 and 2, and the root is 1.15417. 1.15417, so we're good to go. If you want to use this method all the way through, feel free to. It's probably good to do a couple of iterations to get a feel for how it works, but once you get a feel for how it works, just let a computer do the computation. So I hope this was helpful, and I'll see you next video.